Welcome back. In this video, we're going to look at examples of solving improper integrals. Let's get to it. All right, so here's our first example. We have the integral from 1 to infinity of e to the power of negative x times dx. Now, this is an improper integral because one of our bounds of integration is infinite. Specifically, our upper bound is infinity. And so we need to treat this integral a little bit differently than we would treat a normal definite integral. What we're going to do is introduce a limit to this integral in order to solve it. And so here's what that looks like. This will be equal to the integral from 1 to infinity, but we're going to replace infinity with a different variable. We're just going to make it b, and that will be of e to the negative power of x times dx. Now for that upper bound that we replaced with b, we are then going to introduce a limit as b approaches infinity. Okay, so we replace infinity with b, and then we take the limit as b approaches infinity instead. And this is going to allow us to evaluate this improper integral. And so we can continue on with our integration process here, and then we will worry about evaluating the limit. And so we need to integrate e to the power of negative x. And since e is raised to a power that is not just x, we should use u substitution to solve this integral. Specifically, we will set u equal to negative x, that exponent, and rewrite this integral in terms of u. So we need to take the derivative of u, so we'll have du dx is equal to negative 1, because the derivative of x to the first power is equal to its coefficient, which is negative 1. And then if we solve for du, by multiplying both sides by dx, we will have that du is equal to negative dx. Now whatever du is equal to, we need to be able to find that within our integral. However, I don't see negative dx in our integral, I just see positive dx. And so if I multiply both sides by negative 1, we'll have negative du is equal to dx, and now we can replace dx with negative du. So we'll have that this is equal to the limit as b approaches infinity, and that will be of the integral from x equals 1 to x equals b of e to the power of u times negative du, right? We replaced negative x with u because that's what we set it equal to, and we replaced dx with negative du because that's what we found that was equal to. Now I wrote our bounds of integration as x equals because I want you to remember that these are values of x and not values of u. We will integrate in terms of u and then write our answer back in terms of x. And so if we pull that negative out front and then integrate e to the power of u, this will be equal to the limit as b approaches infinity of negative e to the power of u evaluated from x equals 1 to x equals b. Okay, so the integral of e to the power of u is just itself, and then we pulled that negative out front, and then we have our same bounds of integration. Now if we replace u with what we set it equal to, that was negative x, this will be equal to the limit as b approaches infinity of negative e to the power of negative x evaluated from 1 to b. And now if I clean up my work here, we can evaluate this expression at b and subtract the evaluation at 1, and then we can evaluate our limit. So this will be equal to the limit as b approaches infinity of negative e to the power of negative b minus negative e to the power of negative 1. Now these two negatives will cancel out to become positive, so we will have plus e to the negative first power. And then if we moved each of these e's with negative exponents to the denominator so that their exponents are positive, then we'd have that this is equal to the limit as b approaches infinity of negative 1 divided by e to the power of b plus 1 divided by e to the power of positive 1. All right, and so now we can evaluate the limit as b approaches infinity for these two terms. And so if we do that, this is going to be equal to negative 1 divided by e to the power of b as b gets larger. Now, as you take e to a higher and higher power towards infinity, the value of that term is going to get larger, right? E to the power of 1 is just e, but e to the power of 10 is going to be even bigger, and e to the power of 100 gets even larger. And so e to the power of b, where b is approaching infinity, is just equal to infinity. And so we could rewrite this to be negative 1 divided by infinity, and then the limit of a constant 1 divided by e is just going to be that constant. So then we have plus 1 divided by e. But remember, when you have a fixed value divided by an infinite value, that term is going to become 0. When you increase the denominator of a fraction, that fraction is going to become smaller and smaller towards 0. Right? -1 divided by 10 is equal to -0.1, but -1 divided by 100, which is a larger denominator, would be equal to -0.01. And so this is closer to 0 than this value, and you would continue to get even closer to 0 as that denominator increases. And so we will say that this is equal to 0 plus 1 divided by e, which tells us that this is equal to 1 divided by e. And so that is the solution to this improper integral. Now there's one more thing that you could write here, and that is when an improper integral is equal to a finite value, meaning that you found a specific value that it's equal to, we say that the improper integral converges. And so you could write down that it converges. All that means is that the integral is equal to a specific value. It's not equal to infinity or negative infinity, which aren't specific values. If your integral is equal to an infinite value, then you would say that your integral diverges. Okay? And so let's take a look at another example. All right, so here's our next example. We have the integral from 1 to infinity of 1 divided by the square root of x times dx. Now, once again, this is an improper integral because the upper bound is an infinite bound. The moment you see either infinity or negative infinity for one of your bounds, you know you have an improper integral, and so you will need to introduce a limit in order to solve it. So this is going to be equal to the integral from 1 to b. We're going to replace infinity with b, and then have the same integrand of 1 divided by the square root of x times dx, and then we will take the limit of that integral as b approaches infinity, just like we did in the previous example. All right, and so now we can work on integrating this function. Note that 1 divided by the square root of x is the same as 1 divided by x to the 1/2 power, and so if I rewrite that, we'll have x to the 1/2 power, but then we can move that to the numerator by making the exponent negative, and so then we would have x to the negative 1/2 power. All right, so that is the same as 1 divided by the square root of x, and now we can see how we can integrate this by using the power rule of integration. We'll add 1 to that exponent and then divide by that new exponent. So this will be equal to the limit as b approaches infinity of x to the 1/2 power divided by 1/2, evaluated from 1 to b. Right? -1/2 plus 1 is positive 1/2, and then you will divide by positive 1/2. Now, if we rewrite this a little bit, dividing by 1/2 is the same as multiplying by 2, right? Dividing by a fraction is the same as multiplying by the reciprocal of that fraction, and the reciprocal of 1/2 is 2, and then we can rewrite our 1/2 power to be the square root of x again. So this will be equal to the limit as b approaches infinity of 2 times the square root of x, evaluated from 1 to b. All right, so now if we evaluate this expression at b and subtract the evaluation at 1, we will have the following. This will be equal to the limit as b approaches infinity of 2 times the square root of b minus 2 times the square root of 1. Now the square root of 1 is just 1, so we have 1 times 2, so this is equal to the limit as b approaches infinity of 2 times the square root of b minus 2. And now what happens to this expression as b approaches infinity? Well, we have 2 times the square root of b, and as b gets larger within this square root function, the value of that square root function will also get larger, right? The square root of 9 is 3, the square root of 16 is 4, the square root of 100 is 10, so the larger b gets, the larger the value of that square root will also get. And so we can say that the square root of b, as b approaches infinity, will be infinity, and so this would be equal to 2 times infinity minus 2, because the limit of a constant is just that constant, but 2 times infinity is still infinity, and so this is equal to infinity minus 2, but if you subtract 2 from infinity, you still have infinity, and so this is equal to infinity. And so infinity is the solution to our improper integral. However, it's not a specific value. It does not converge to a finite number. And so we will say that this improper integral diverges. All right? It does not converge to one value. It's equal to infinity. All right, let's take a look at another example. So here's our next example. We have the integral from negative infinity to positive 3 of 2x divided by x squared plus 1 times dx. All right, so once again, we know we have an improper integral because our lower bound is negative infinity. We have an infinite bound, and so we have an improper integral. So we need to rewrite our integral by introducing a limit for that lower bound. So this is going to be equal to the integral from a to 3. We're going to replace negative infinity with a. Now you could choose to use b again, but for me, I prefer to change the lower bound to a and the upper bound to b. So depending on where the infinite bound is, I like to change what variable I'm working with. It really doesn't matter. It could be a, b, c, d, any letter you like, but I like to use a. And then the rest of our integral will stay the same. So we have 2x divided by x squared plus 1 times dx. But then don't forget to add a limit. We'll have the limit as a approaches negative infinity. So we replace negative infinity with a and then introduce the limit for a as it approaches negative infinity. Okay, so now we can work on solving this integral here. We have 2x in the numerator and x squared plus 1 in the denominator. So how could we solve this integral? Well, one of the things you want to be on the lookout for is if you can use u substitution. And u substitution is useful for integrating composite functions or when you see a function and its derivative in the integral. And so in this case, do we see a function and its derivative? Well, in the denominator here, we have x squared plus 1, and in the numerator, we have 2x, and we know that the derivative of an x squared function will be a function with x to the first power. And so, u substitution is going to work here. If we set u equal to x squared plus 1, its derivative will be in the numerator, and so everything should work out. So if we set u equal to x squared plus 1, and we take the derivative, we'll have du dx is equal to 2x, because the derivative of x squared using the power rule will be 2x if we multiply that exponent down and subtract 1 from the exponent. So we have 2x to the first power, and the derivative of 1 is just 0, since the derivative of all constants is 0. Now if we solve for du by multiplying both sides by dx, we will have du is equal to 2x dx. And so now, whatever du is equal to, we need to be able to find that within our integral. And so 2x dx is right here. We have 2x and dx. And so we're good here. We can rewrite our integral in terms of u. So this will be equal to the limit as a approaches negative infinity of the integral from x equals a to x equals 3 of 1 divided by u times du. Right, we replaced x squared plus 1 with u because that's what we set it equal to, and we replaced 2x dx with du because that's what we found that was equal to. And once again, just like with one of our other examples, I wrote our bounds of integration to be values of x because that's what they are. You just want to remember that these are not values of u, that you need to rewrite the solution to this integral back in terms of x before you plug in those bounds of integration and ultimately evaluate your limit. And so let's solve our integral here. We know that the integral of 1 divided by u is equal to the natural log of the absolute value of u from the log rule of integration. So this will be equal to the limit as a approaches negative infinity of the natural log of the absolute value of u evaluated from x equals a to x equals 3. Now if we replace u with what we set it equal to, then this will be equal to the limit as a approaches negative infinity of the natural log of the absolute value of x squared plus 1 evaluated from a to 3. All right, so now if I clean up my work here, let's evaluate this expression at each of our bounds. We'll plug 3 in and then subtract plugging a in. So this will be equal to the limit as a approaches negative infinity of the natural log of the absolute value of 3 squared plus 1 minus the natural log of the absolute value of a squared plus 1. All right, now 3 squared is equal to 9, and 9 plus 1 is 10. And so this is equal to the limit as a approaches negative infinity of the natural log of 10 minus the natural log of the absolute value of a squared plus 1. All right, now the limit as a approaches negative infinity of this constant, the natural log of 10, is just going to be equal to the natural log of 10. So this is equal to the natural log of 10, and then we will subtract the limit of this natural log function. And so now what happens to this term or this expression as a approaches negative infinity? We'll note that a is being squared, and so even though a is becoming a larger and larger negative value, it's just going to be squared, which makes it positive. And so a squared is just becoming a larger and larger positive value that we are then adding to 1. And so this whole expression, a squared plus 1, is just infinity. And then the natural log of infinity is just going to be infinity. As you plug in larger and larger values into the natural log function, it is going to output larger and larger values. And you could test that in your calculator if you'd like. The natural log of 100 is going to be greater than the natural log of 10. And then the natural log of 1,000 would be even greater than that. So as you plug in larger and larger values, the natural log function outputs larger values. And so the natural log of the absolute value of a squared plus 1 is just going to become infinity. So now we have the natural log of 10 minus infinity, but this constant is going to be pretty insignificant to negative infinity, and so we can completely ignore that constant and say that this is equal to negative infinity. And so negative infinity is the solution to this integral. However, that's not a specific value or a finite number, and so we will say that this improper integral diverges. All right, it does not converge to a specific number. Okay, let's look at another example. So here's our next example. We have the integral from 4 to infinity of 1 divided by x minus 2 quantity cubed, and then we have dx. All right, so once again, this is an improper integral because the upper bound is an infinite bound of infinity. And so let's rewrite this integral using a limit. This will be equal to the integral from 4 to b. I'm going to replace our upper limit of infinity with b, and then we will have the same integrand of 1 divided by x minus 2 cubed times dx. And then don't forget to introduce a limit, so we'll have the limit as b approaches infinity. Okay, so we replaced infinity with b, and now we take the limit as b approaches infinity. So now we can work on integrating this integral, and in this case we have this composite function of x minus 2 cubed, and so I'm thinking we can use u substitution here to solve this integral. If we set u equal to x minus 2, its derivative will just be a constant, and so that's going to work just fine. We will set u equal to x minus 2, which means that the derivative, du dx, will be equal to 1, because the derivative of x is 1, and the derivative of negative 2 is 0. And so that means that du will be equal to dx if we multiply both sides by dx, and so we can rewrite this integral in terms of u. This will be equal to the limit as b approaches infinity of the integral from x equals 4 to x equals b of 1 divided by u cubed times du. Okay, so we replaced x minus 2 with u because that's what we set it equal to, and we replaced dx with du because that's what we found that that was equal to. And then once again, I wrote our bounds of integration as values of x so that we don't forget that we can't plug in those bounds into our integral in terms of u. Okay, so let's integrate 1 divided by u cubed. That would be the same as u to the negative third power if we moved that to the numerator by making that exponent negative. And now we can use the power rule of integration and add 1 to that exponent and then divide by the new exponent. And so this will be equal to the limit as b approaches infinity of u to the negative second power divided by negative 2 evaluated from x equals 4 to x equals b. Right, so we added 1 to our exponent. Negative 3 plus 1 is negative 2, and then we divided by that new exponent of negative 2. Now, if we rewrite this a little bit, we can move this negative to the numerator, and then u to the negative second power can move to the denominator by making that exponent positive. And so this is equal to the limit as b approaches infinity of negative 1 divided by 2 times u squared, and that is evaluated from x equals 4 to x equals b. Now we can rewrite this again by replacing u with what we set it equal to, and so u is equal to x minus 2, which means that this will be equal to the limit as b approaches infinity of negative 1 divided by 2 times x minus 2 squared evaluated from 4 to b. All right, so now if I clean up my work here, we can evaluate this expression at b and then subtract the evaluation at 4. So we will have that this is equal to the limit as b approaches infinity of negative 1 divided by 2 times b minus 2 squared. And then we will subtract negative 1 divided by 2 times 4 minus 2 squared. All right, now these two negatives will cancel out to become positive, so I'll just rewrite that. We'll have plus 1 divided by 2 times 4 minus 2 squared. Now 4 minus 2 is equal to 2, and 2 squared is 4, times 2 is 8, and so this will be equal to the limit as b approaches infinity of negative 1 divided by 2 times b minus 2 squared plus 1/8. Okay, and so now we can take the limit of this expression as b approaches infinity, and so I'll continue that work up here. This will be equal to negative 1 divided by 2 times b minus 2 squared as b gets larger towards infinity. Now as b becomes infinity, we'll have infinity minus 2, and so infinity minus 2 is still infinity, and then we have infinity squared, and so infinity squared is also still infinity. We're just making a very large number even larger. And so then we have infinity times 2, which is still infinity. And so we have negative 1 divided by infinity plus the limit of 1/8 as b approaches infinity, and the limit of any constant is just that constant. So we have plus 1/8. Now we saw this in a previous example, but when you have a fixed value divided by an increasing denominator, or you have a fixed value divided by an infinite value, then that will become 0. As that denominator gets larger, that fraction will become 0. It will get closer and closer to being 0, and so we will say that this is equal to 0 plus 1/8, which is just equal to 1/8. And so 1/8 is the solution to this integral, and so we can say that that improper integral converges. It converges to a specific value. It's not infinity or negative infinity. Okay, let's look at a different example. All right, so next up we have the integral from 2 to 6 of 1 divided by the square root of x minus 2 times dx. Now initially this may not seem like an improper integral. It looks like an integral that we have been able to solve up until this point. However, this function is not defined for all the values that we are going to be integrating between, and that includes those bounds of integration. Specifically, take a look at this lower bound. If you plug 2 into this function here, we have 1 divided by the square root of 2 minus 2, and that's equal to 0, and so you have the square root of 0, which is equal to 0, in the denominator. So you have 1 divided by 0, which is an undefined value, and so this function is not defined at x equals 2. And so integrating it from 2 to 6 makes this an improper integral. We are integrating over an interval where one of those bounds of integration is a value for which the function is not defined. In fact, we would call that an infinite discontinuity, because if you were to look at a one-sided limit for that function at 2, it would be equal to either infinity or negative infinity. I think in this case, if you looked at the limit as x approaches 2 from the right of this function, it would be equal to infinity. You don't need to know that. As long as you realize that this function is not defined at one of your bounds or a value between your bounds, then you know you have an improper integral where you need to introduce a limit in order to solve it. And so in this case, since we know our lower bound is where that infinite discontinuity is, or where our function is undefined, that is what we're going to replace with a variable and then have the limit of that variable as it approaches 2. And specifically, we're going to have a one-sided limit where we approach that value from the right. Whenever you replace a lower bound, when you have an infinite discontinuity or undefined value, you're going to have the limit from the right of that value. And when you replace an upper bound, let's say if this was undefined at 6, then you would replace that with a value and take the limit as it approaches 6 from the left. So an upper bound you would replace with a limit from the left, and a lower bound you would replace with a limit from the right. So now let's write that out. Let's see what that actually looks like. If we rewrite this integral, we'll have the integral from a to 6. Once again, when I rewrite a lower bound, I use a. And then we have the same integrand, the square root of x minus 2 in the denominator, times dx. And then our limit will be as a approaches 2 from the right. We replace 2 with a, so we have the limit as a approaches 2, and since that was a lower bound, we look at it from the right. All right, and so now that we have rewritten our integral with that limit, let's work on solving the integral that we have here. Now in this case, we have a composite function in the denominator. We have the square root of x minus 2, the square root being the outside function and x minus 2 being the inside function. And so u substitution might be helpful here. We just need to make sure that if we set u equal to that inside function, that its derivative can be found in the integral. And in this case it can, because the derivative of x to the first power is just going to be a constant. And so we'll set u equal to x minus 2, which means that the derivative, du dx, will be equal to 1, because the derivative of x is 1 and the derivative of negative 2 is 0. I believe this is the exact same derivative we took in the previous example. But either way, du will be equal to dx if we multiply both sides by dx. And so now we can rewrite this integral in terms of u. So we'll have that this is equal to the limit as a approaches 2 from the right of the integral from x equals a to x equals 6 of 1 divided by the square root of u times du. Okay, so we replaced x minus 2 with u because that's what we set it equal to, and we replaced dx with du because that's what that is equal to. All right, so now let's integrate. 1 divided by the square root of u would be 1 divided by u to the 1/2 power, and then we can move that power to the numerator, and so we'll have u to the negative 1/2 power. All right, so we have u to the negative 1/2 power, and now we can use the power rule of integration to integrate this. So this will be equal to the limit as a approaches 2 from the right of u to the positive 1/2 power divided by 1/2 evaluated from x equals a to x equals 6, right? Negative 1/2 plus 1 is positive 1/2, and then we divide by positive 1/2. Now if we simplify this a little bit, remember that dividing by a fraction is the same as multiplying by its reciprocal, and so dividing by 1/2 is the same as multiplying by 2. So this is equal to the limit as a approaches 2 from the right of 2 times u to the 1/2 power, which we can rewrite as the square root of u. And that is evaluated from x equals a to x equals 6. Now before we evaluate this at our bounds, u needs to be expressed in terms of x, and u is equal to x minus 2. So let's substitute back. We will have that this is equal to the limit as a approaches 2 from the right of 2 times the square root of x minus 2 evaluated from a to 6. And now if I clean up my work, we can evaluate this expression at 6 and then subtract the evaluation at a. So this is going to be equal to the limit as a approaches 2 from the right of 2 times the square root of 6 minus 2 times the square root of a minus 2. Now 6 minus 2 is 4, and the square root of 4 is 2. So we have 2 times 2, which is 4. So this is equal to the limit as a approaches 2 from the right of 4 minus 2 times the square root of a minus 2. Now since we have a one-sided limit of a value that is not infinite, let's just plug in 2 into this expression and see what happens. If we have an undefined value somewhere, then we will have to take a look at values of a close to 2 from the right side. But I have a feeling that in this case, we are just going to be able to plug 2 right into this expression. And so if we do that, this will be equal to 4 minus 2 times the square root of 2 minus 2. 2 minus 2 is 0, so the square root of 0 is 0. And so we have 2 times 0. And so this whole value is 0, which just leaves us with 4. 4 is the solution to this improper integral. Okay, so we actually didn't have to do anything too fancy with this limit. We just had a one-sided limit of 2 from the right side, but we were able to plug in 2 and get a real value. And so we can say that this improper integral converges. It is equal to a specific number of 4. Okay, let's look at one more example for this video. All right, so here's our final example. We have the integral from negative infinity to positive infinity of 1 divided by x squared plus 1 times dx. Now in this case, both of our bounds are infinite bounds. We have negative infinity and infinity. So hopefully you're able to identify that this is an improper integral. It's pretty obvious when both bounds are infinite. And so we're going to need to rewrite this integral using limits. But before we can do that, we actually need to split up this integral first. And so what we're going to do is just pick some value between negative infinity and infinity for which this function is defined for, which in this case 1 divided by x squared plus 1 is going to be defined for all values of x. And so we could pick any value we'd like, but I think it's pretty easy to evaluate things at 0. And so here's what I'm going to do. I'm going to rewrite this integral to be the integral from negative infinity to 0 of 1 divided by x squared plus 1 times dx plus the integral from 0 to infinity of 1 divided by x squared plus 1 times dx. All right, so the convenient value of x that I picked is 0, and so that's going to be that midpoint that we use to break up our integral into two integrals. We have negative infinity to 0, and then 0 to infinity. And now we can rewrite these two integrals with a limit for our infinite bounds. So if we do that, this will be equal to the integral from a to 0 of 1 divided by x squared plus 1 dx, and then we will have the limit as a approaches negative infinity, and we will add that to the integral from 0 to b of 1 divided by x squared plus 1 times dx, and then we will have the limit as b approaches positive infinity. Okay, so if I clean up my work here, we can now work on solving our integrals. Now we have the same integral in both cases, except they have different bounds of integration, and 1 divided by x squared plus 1 is actually a very simple function to integrate. We have a special rule for that function. We know that the integral of 1 divided by x squared plus 1 dx is equal to arctangent of x. And if we were working with indefinite integrals, we would have plus c, but we don't really need to worry about that since we have definite integrals. But this is one of our rules for integrating into an inverse trig function. 1 divided by x squared plus 1 is the arctangent function. And this stems from the more complicated version that the integral of 1 divided by u squared plus a squared times du is equal to 1 divided by a times arctangent of u divided by a plus c. But you don't need to worry about that in this case because we just have 1 divided by x squared plus 1, but this is maybe the rule that you were used to seeing or you were more familiar with. But anyway, let's integrate our two integrals here. This will be equal to the limit as a approaches negative infinity of arctangent of x evaluated from a to 0 plus the limit as b approaches infinity of arctangent of x evaluated from 0 to b. Now if we evaluate arctangent for both sets of these bounds, we will have that this is equal to the limit as a approaches negative infinity of arctangent of 0 minus arctangent of a plus the limit as b approaches infinity of arctangent of b minus arctangent of 0. Okay, so we plugged in our upper bounds into arctangent and then subtracted, plugging in the lower bounds. Now if I clean up my work here, arctangent of 0, which we have right here and right here, is just equal to 0. If you plug that into your calculator, arctangent of 0 is 0. And so this is equal to the limit as a approaches negative infinity of 0, but we don't really need to write that, minus arctangent of a, and then we will add that to the limit as b approaches positive infinity of arctangent of b minus 0. But once again, we don't really need to write that, and so we just have arctangent of b. All right, and so now we have these two limits that we can evaluate. Let's start with our first one here. We have the limit as a approaches negative infinity for negative arctangent of a. And so now if a is approaching negative infinity, what happens to the arctangent function? Well, if you were to look at the graph of the arctangent function, it is shaped a bit like this, where it has two horizontal asymptotes, one of them up here and one of them down here, where this horizontal asymptote is at positive pi divided by 2, and this horizontal asymptote is at negative pi divided by 2. And those are both values of y, of course. And so as a approaches negative infinity, and remember that a is a value of x, if we look at our graph as x approaches negative infinity, we are slowly approaching that horizontal asymptote, right? So we are slowly getting closer to that value of negative pi divided by 2. And so that's actually going to be the limit of arctangent as a approaches negative infinity. It's going to be negative pi divided by 2. And so this will be equal to negative pi divided by 2. Don't forget that you have this negative out front. And then we will add that to the limit as b approaches infinity of arctangent of b. Now if we look in the positive direction, as we pick larger and larger values of x, because b does represent values of x, the arctangent function gets closer to this horizontal asymptote of y equals positive pi divided by 2. And so we would say that the limit as this function approaches positive infinity would be positive pi divided by 2. So this limit is pi divided by 2, so we will add pi divided by 2. All right, and so if you have access to a graphing calculator and you can graph the arctangent function, that might be one way that you could determine these values. But other than that, if you don't have access to this graph, I know that this can be a little bit of a tricky problem to solve. And so that's where it's going to become handy for you to be familiar with your inverse trigonometric functions. And so if you knew that the arctangent function had a range of negative pi over 2 to pi over 2, that might be an indicator that you have some horizontal asymptotes and that the limit as you approach infinity or negative infinity are going to be the values of those horizontal asymptotes. Okay, but hopefully you have the ability to graph the function and take a look at it, because this is ultimately going to be the most helpful to evaluating limits like these. And if you ever truly get stuck, you can always choose larger and larger values of b to plug into the arctangent function, or smaller and smaller values to plug into it, and you could see what value it approaches. Now, it's most likely that your calculator is going to output decimal values for that, so you could still get the same answer, but it would be in a decimal form rather than what we are going to get here. And so that's another method that could also work. But if we simplify our answer here, negative pi divided by 2 is positive pi divided by 2, so this is equal to pi divided by 2 plus pi divided by 2, which is equal to pi. And so pi is the solution to this improper integral, and since that is a set value, we will say that this improper integral converges. Okay? It converges to a set number. All right, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.